Greetings, carbon-based life forms. I'm here to present CEP's most coveted award. It's April Fool's Award, the Jackson, an elegant lump of coal to the person or persons who have made a distinctive effort to rid humanity of that curse that has led to increasing productivity, remarkable decreases in subsistence living, hand-to-mouth living, and led to comfortable living for most, the curse of fossil fuels. Early in the voting, the leaders of the National Science Teachers Association appeared to be the clear winners. They prudently demanded that representatives of the CO2 coalition and their displays be removed from a conference of science teachers. The troublemakers espoused the radical idea that carbon dioxide is necessary for all green plant life, thus all life. What a horrible idea. But in the end, the voting came a tremendous surge for one man. He was the honor student in physics and electrical engineering. He began his professional career teaching systems theory and telecommunications. But politics called. As the awardee climbed the political ladder, China abandoned its policy of strict control of economic activity, and prosperity flourished, in part due to fossil fuels. Much of South Asia followed.
All right, thank you. Thank you.
Our World in Data reports that since 1990, we have seen the most remarkable decline in extreme poverty ever. Also, China produces more carbon dioxide than the US and the EU combined. India is following suit. But our April Fool's recipient has declared that fossil fuels are the enemy of humanity, and he intends to lead the world's premier international organization founded in the hope for humanity against the use of fossil fuels regardless of the consequences. The 2023 recipient of the April Fool's Award is UN Attorney General Antonio Leave It in the Ground Guterres. I've just been informed Mr. Guterres will not be here to accept the award. Apparently, he could not get renewable fuel for his jets. One of the most misunderstood concepts, I think, in modern science is the greenhouse effect. John Tyndall began in 1859 to understand what he became the greenhouse effect. He was trying to answer a critical question. Why is the Earth warm enough to support life? Why don't the land masses of the Earth freeze each night? And he discovered that certain gases allow the solar energy to pass through, but stop or slow down the loss of heat at night. Water vapor is by far the dominant gas. CO2 is carbon dioxide is secondary. He named these gases greenhouse gases. The findings were quickly misunderstood and exaggerated in efforts to try to explain what causes the end of ice ages, which other scientists were discovering. It's very interesting that the EPA cites the erroneous errors by the other scientists in its endangerment finding that carbon dioxide endangers public health and welfare, and ignores the actual work of John Tyndall or the retractions of the scientists who realized they were wrong. In 1979, a prestigious group of meteorologists gathered to produce a report to examine what will happen as Asia and other countries begin to expand their production of carbon dioxide, their use of fossil fuels. The meeting produced a report called the Charney Report. And the report states very clearly that meeting was dominated by those who developed numerical forecasting of weather and applied it to climate. Some others objected, such as the atmospheric physicist Richard Lindzen. The modelers assumed that with increasing temperature from CO2, relative humidity would remain constant, thus increasing the amount of water vapor in the atmosphere. This was an assumption, no evidence, pure speculation. Since then, starting in 1979, we had the advent of satellite measurements. Roy Spencer and John Christie found that they could use measurements of radiation from oxygen to estimate temperature trends. They published this in 1990. Initially, this was a great breakthrough and was well received. But as the fear of carbon dioxide grew, their funding dried up. They are no longer funded to produce reports, but the satellite measurements continue. The 1990 initial report of the UN Intergovernmental Panel on Climate Change showed changing temperatures of since the last ice age and over the last 1,000 years. The latter temperatures were largely based on what was observed in Middle England and what was reported by geologists. Shortly thereafter, modelers from the UK Met Office took over the IPCC reports. These were numerical weather modeling specialists. And they picked up and changed the reports to reflect the temperatures since the last ice age and over the temperatures for since about 1880. It doesn't go back to the last ice age. And the UN IPCC reports still continue with that period. They have nothing to do with history, climate history. Yet, through careful and persistent measurements, we have a tremendous advances in our understanding of what is occurring in the atmosphere. And we cannot find the increase in water vapor that the climate modelers say it should be there. Dr. Howard Hayden will report on some of the advances in measurements in the atmosphere, and then I'll conclude with a report on some of the advances in understanding the history of the changing Earth's temperature from the abyss.
Thank you, folks. I think everybody ought to give a big hand to Jeremy because he does a terrific job running this. I'm going to be talking about some technical stuff, and before some of you go to sleep, I thought I would give you a slight test of perspicacity on a subject that has nothing to do with climate. But once upon a time, very early in my career at the University of Connecticut, I had the job of driving 5 Russian scientists, probably including one from the KGB, down from Connecticut to NYU in Manhattan. On the way down there, Fedorenko tapped me on the shoulder and asked if we could drive through Harlem. Well, the only thing I knew about Harlem was that I'd get off the road at 125th and go driving around. So we did that. And they didn't find any cops beating up on black people with billy clubs or anything, so okay, let's just go down to NYU. So we got down to NYU, and I was actually scheduled to go do something later on out on Long Island, but I had some time to kill, so I told these gentlemen when they got checked in that I would be tickled to drive them anywhere they would like to go in Manhattan. I couldn't bring them back, but I'll take you there and then you can just do what you're going to do and then come back. So your job, should you decide to accept it, is to shout out where you think they would like to go. Macy's. Okay. I'm going to be talking about the greenhouse effect, and it's more in the sense of understanding it than anything else. So here we go. The first thing I'm going to do is say that the greenhouse effect is real. And I spent a lot of time arguing with people who lovingly call themselves skeptics. And I've had a lot of them say the greenhouse effect can't be real. And I'm going to describe how it's real. But that does not mean that the additional greenhouse effect from adding more CO2 is going to cause any problems, or that we're having a climate crisis. We're not having a climate crisis, but that doesn't mean that the greenhouse effect is not real. The greenhouse effect is real, but it's no big deal. But what it does mean is that the greenhouse effect must be understood, especially by skeptics. And that is, the point there is that you should never support a strong case with weak arguments. And there are all these people out there who are calling themselves skeptics. They don't know their right hand from their left, but they're so easy for the climate establishment, as it were, to laugh out of the city. So this is dedicated toward getting you to understand what the greenhouse effect is all about. So I've had some battles with some of these naysayers, and they don't all understand some basic science. And I'm going to bring up 2 of these things before I get into the technical stuff. They say, these are 2 things that they have said. There are others. The atmosphere can't radiate toward a warmer surface. In other words, the surface is warm, the atmosphere is cooler. How can that possibly take place without, excuse me, without doing violence to the second law of thermodynamics? And the other argument is that the radiation that goes into space is just the radiation that leaves the surface minus some stuff taken out by atmospheric gases. Now I'll undertake I'm now going to take the first of those two questions. The atmosphere can't radiate toward the warmer surface. Now, you may not realize it, but the people who say that are busy ascribing intelligence, indeed brilliance, to molecules. Now picture yourself as being a molecule that has absorbed some infrared radiation from the Earth. Now what are you going to do with that energy that you've got absorbed? I can't radiate it that direction. I mean, it's that level of stuff that I find myself battling with other people about, because they just don't quite understand second law of thermodynamics. Okay, the radiation to space is just the surface radiation except for the IR removed by greenhouse gases. So, here is the spectrum emitted to space as calculated by the IPCC in their first assessment report, 1990. Here is the radiation to space measured by the Nimbus satellite in 1970, 20 years before the IPCC first report. And what I want to do is to call your attention to the region right in there around the 15 microns wavelength, or around 666, the number of the beast, says Willie. 666 inverse centimeters, that's just reciprocal wavelength. We do that because energy is proportional to that. Anyway, you may notice that the IPCC was finding that the amount of radiation going into space was about 0 at that particular wavelength, whereas if you look at the actual measurement that they should have known about, because it was done 20 years sooner, it's not anywhere near 0. It's small compared to maybe what you think it ought to be. But I also want to call your attention to, in the right-hand drawing up there, right about at the tip of the arrow, but a little bit beyond, there's a spike. And that is a very important spike to understand. I'm going to talk a little, we're going to be talking about the radiation to space. And you got to understand that the infrared that goes out to space is the one and only way that the Earth can shed heat that it has absorbed from the sun. Okay? It's the one and only. There is no other. You can ask for it by name. So, we're going to talk about the planetary heat balance. The IR to space is equal to the heat absorbed from the sun. That's a law that is more general than just the Earth. It applies to all planets, all comets, all asteroids, all moons, all little rocks absorbing, that are orbiting the sun. Okay? And here is a statement that is worthy of understanding. If you have a climate model that cannot properly account for that spectrum, detail by detail, it's as useful as a screen door in a submarine. By the way, I'm not going to be talking about politics in here. My parents taught me a very good social rule, which is if you don't have anything nice to say about anybody, don't say it. I repeat, I will not be talking about politicians. Okay, now where are we going to start in this little discussion about how the greenhouse effect works? We're going to come back to things here. We're going to start at the surface. The surface radiation amounts to what's called black body radiation. It's a smooth distribution over a whole bunch of wavelengths. That's what leaves you, or the table, okay? It's temperature dependent, but it's a nice smooth curve. This is what goes out into space. That jagged line. So the big question is, how does that happen? What happens in the atmosphere between the surface and the upper atmosphere where radiation heads off into space? And it's going to be just a little discussion about how all that works. Incidentally, I'm going to point out that, well, no, it isn't in this graph. I didn't say that. Strike that. You might think that what the process by which the IR is transformed from the smooth distribution on the left to the jagged distribution on the right is that it's just absorption of certain wavelengths by atmospheric gases, but you would not be right. Life is not that simple, and we're going to come to a proof of this that really ought to be understood even by politicians. I'm going to call your attention to two representations of the spectrum this is the absorption spectrum of carbon dioxide. It's measured in units on the vertical axis as a cross section, and on the horizontal axis, well, let's see, the one on the right is in wavelengths, the one on the left is in wave numbers, which is reciprocal wavelength, but they're characterized by a central peak there. The scale on the left is logarithmic. It goes 10 to the minus 18 square centimeters, and then it jumps down 2 factors of 10 to 10 to the minus 20, 2 more factors of 10 down to 10 to the minus 22, and so forth. Now let me explain what I mean by a cross section. Suppose you have a tube, and inside this tube you have a bunch of molecules or something that can be defined by a cross section. And you fire something in from this end of the tube, and then you ask, well, what is the probability that this thing that you fired in at this end comes out at the far end? Or better yet, what's the probability that it does not? So if you have a bunch, let's say 1,000 different targets in there, each one has a cross section which we call sigma, then 10 times sigma, or what I say, 1,000 times sigma is the total area that you have for this projectile or whatever it is to go through to hit. So the probability is the number of those targets in there times their cross section divided by the area of our circle, of our pipe, okay? So that's how you measure it. I did a lot of that when I was a grad student. And you don't need to know except that it's just a description of how big in this case, how big the molecule looks to incoming radiation at various wavelengths, okay? So this super sharp peak there, let me tell you what that means. I'll just tell you what the answer is, and you can write it out on your napkin. That IR, that wavelength, 15 microns, travels this far. That's called the mean free path. It's 20 centimeters before it's absorbed. I hope this doesn't come as a big surprise to you, but there are a lot of 20 centimeters between here and the top of the atmosphere. Now, what do you think that means for the amount of radiation from that IR? How much of that radiation is going to get through the atmosphere? A big fat zero. Okay. Another thing I want to point out, by the way, this is just a little bit of very, very elementary quantum mechanics. Atoms and molecules are kind of like this. They have energy levels that they can exist in. They can have this much energy or that much energy or that much energy, but nothing in between. They're called these energy levels. And in, let's say, the hydrogen atom, if you look at the spectrum, now the spectrum is telling you that there's light that comes out that has the energy difference between two states. The hydrogen spectrum, you can only see 4 or 5 lines with your naked eye. Okay? When you get to molecules, you have more states. When you get to a solid, you have basically an infinitude of states. Okay? Anyway, with the molecules, if you look at the logarithmic graph there, well, you can see a bunch of bumps in the linear graph at the right, but in the logarithmic scale, I don't know if you can see that, but all that fuzz in there is a whole bunch of separate lines. Each one of those is representing the energy difference between this state and some other state. Tremendous number of them, all in a small region. It's called a band. I'm not sure how it works in eastern Boston. It may be banned in Boston. Okay, so you can see where the strongest absorption is going to be, and IR at that 15 micron peak has only, it's 20 centimeters mean free path. You're not going to find it in the upper atmosphere. Now we're going to look at the actual data. This is the IR mission to space. One of them is the data from the Nimbus satellite flying over Guam. Another one is a satellite flying over the Sahara. I've labeled on the right-hand graph CO2. That's the CO2 absorption band, all that yellow stuff from the previous graph. Okay. Call your attention to that spike right there in the Guam, and it's also in the Sahara. The 15 micron spike. Explain, please, how that can be when that IR is so strongly absorbed that it can only go about 20 centimeters before having just about no chance of getting through. Okay, well, we got to explain that. It involves something called the greenhouse effect. The strong peak is in the emitted radiation, and how can that be? How can that IR even get up there? Well, the answer is it doesn't. The important thing here is that the interaction between IR and molecules is not a one and done. In a cubic centimeter, and I'm talking about something more or less the size of a sugar cube, there's a whole bunch of atmospheric molecules. That's 2.5 times 10 to the 19th, for those who don't want to count all the zeros. Those molecules are moving around at more or less Mach 1. They collide, sort of the name of the game. So, here's a greenhouse gas molecule. Could be water vapor, could be CO2. It absorbs some IR from the ground. Now, if that's in that 15 micron peak, it's going to be pretty darn close to the ground. Someone might be up here, some distance away. I don't care. It absorbs some energy. And that energy that's absorbed is involved in a couple of kinds of motion. One of them is this kind of a vibration, and you get this kind of vibration and that kind of vibration. And you also get rotations. Now, the vibrational levels are evenly spaced usually, but the rotational levels are like 1, 3, 5, 7, 9 units apart and that kind of stuff. So anyway, collision comes along, maybe a nitrogen molecule hits our excited CO2 or H2O molecule, and the energy that molecule had tied up in vibration or rotation is suddenly given up to just kinetic energy. Now we got both the CO2 or the whatever it is, the H2O and the nitrogen that hit it, moving a little bit faster, and that increases the temperature incrementally, locally, okay? That's happening on a scale, it is chaos on steroids. It's just really, really crazy what's happening. Well, that's part of the deal. But it's not the whole deal. If that were the whole deal, then there would be none of that spike, that 15 micron spike. There'd be none of that going to outer space. But what does happen is the collisions take place. The collisions that can de-excite molecules can also excite molecules so that they can radiate IR. So just imagine what's happening between the ground and the stratosphere. You got these collisions going on all the time, and in any given time, in any given place, this cubic meter right in here, we have a certain fraction of those molecules that are in an excited state that is possible to radiate from. Okay? They can radiate. So you've got collisionally enhanced excitation, and you've got collisionally, collisional excitation, collisional de-excitation, and so forth. But it's always going on. But there's always a few percent of those molecules can radiate. Now, suppose you were an atomic physicist, molecular physicist, and your job was to calculate what happens on the way up. Well, you do a bunch of calculations. And what would they look like? The thing you would pay attention to is the percentage of these molecules that are in these various excited states as a function of temperature and pressure, because pressure will determine what the mean free path is and so forth. And you have things like Doppler broadening. In other words, those spectral lines get a little bit broader because of motion toward or motion away from each other. And So there's an altitude dependence, and there's also a latitude dependence, because you probably notice that the North Pole's a little colder than the equator, okay? So, let's see. Suppose you didn't know much about this subject. Who would you ask to do the calculation? Al Gore? Okay, you're going to have a hard time with that thing, but you're going to hire somebody who knows a whole lot about molecular physics and radiation, a molecular spectroscopist, or even if your standards drop low, you'd ask a physicist. But before we leave this topic, I want to call your attention to that right-hand graph. Oh no, the left-hand graph. The left-hand graph there, it's the NIMBUS results from Guam. You may notice up in the legend in the upper right, I don't know if you can read it, but there's a dotted line there that says theoretical, okay? 1970. They had a theory. Now, if you would look closely at that, and I don't think you can quite see it from where you are, that theoretical line follows the data damned well, with one exception. Or there's sort of two dips in there, but if you look around 9 microns wavelength, or about 1,100 wave numbers, you'll see a dip in there. That one is due to O3, the ozone. And the people who did the calculation just didn't think to include ozone. I mean, they did the calculation before the measurement. Okay. How did they do that calculation? They knew how to do it in 1970 on the basis of temperature profiles and all that, and all of the spectra that they understood at the time. So you come forward to 2020 or thereabouts, and you come across a paper by Van Wijngaarden and Happer. Now, I've known of Happer's superb reputation since about 1970. He's no slack. He's really good. Anyway, they did some calculations using HITRAN, which is a compilation of the world's most precise data on spectra. They have made a great contribution, but it's not, in a way, what's something you would call new and unique, because they were already doing a pretty good calculation back in 1970. The only thing is, they did the calculation with higher resolution data, and they also did the calculation for many different many different fractions of how much water vapor you got, how much CO2 you got, how much N2O and so forth. They used 5 atmospheric gases. So that's what they did. Okay. There's more. This is something that you've already talked about. Molecular collisions can excite a greenhouse gas into a state that can radiate. It's chaos on steroids. I mean, just crazy stuff going on. You have to do statistics. At all altitudes, all latitudes, there are always greenhouse gases in excited states, typically a few percent, but they diminish as the temperature decreases. That is, you'll talk about some given excited state, how many molecules to have in there. Well, it depends. If you're down at the surface, you got one temperature, or you're up there in the stratosphere, you got a much lower temperature, and there are fewer of those molecules in that state there. But at high altitude, some of that IR can escape to outer space. And it turns out that about 80% of the IR to space comes from high altitude greenhouse gases and from clouds. I remember hearing a talk once upon a time by an astronomer. I think he was from NYU, it might have been from City College. He had his astronomical observatory on top of the physics building in mid-Manhattan. And right now you're probably asking yourself how in thunder that could be, and the answer is he was looking at the skies at a small band of wavelength called the atmospheric window. So he could get information from those stars in that one wavelength band, but it's a small, only about 20% of the radiation that leaves the surface of the Earth goes straight to the atmosphere without being absorbed. He was using that band. So anyway, the greenhouse effect looks like this. The radiation to space, seen on the left, I out, is equal to the surface radiation minus the greenhouse effect, which the IPCC has defined as being essentially the numerical difference between those two quantities. But that spectrum on the right, you got to understand, is not just absorption, it's absorption, emission, and collision, temperature dependent, everything. That's the chaotic thing. But we can assign a number to it. Okay. Now we're going to take a look at the Earth as a whole, kind of, and I've excerpted a little piece of graph from a heat exchange diagram, and it looks like this, that the IN, which is the difference between the incoming sunlight and the reflected sunlight, that's how much we absorb. We reflect about 30% of the radiation, of the incoming visible light. We reflect about 30% into space. Does anybody know how we measure it? It's been measured a long time. By how much we illuminate the moon. Okay? But we know about it. And the IN is the I surface minus G. G being that complicated thing. Okay, there's I out. If IN remains constant, this is extremely important, and it'll be on the exam. If IN remains constant, then if there's any increase in the greenhouse effect, it must be matched exactly by an increase in the I surface. Okay? In other words, if you stop 5 more watts per square meter from going to space, then things will come to an equilibrium when the surface has increased, has warmed up enough to radiate another 5 watts per square meter. Okay. Do not underestimate Al Gore, John Kerry, and Greta Thunberg. Remember I said I don't want to say anything bad. So I will tell you that each of them knows twice as much climate science as the other two put together. Do I hear any objections? Okay. Equilibrium. The infrared that goes into space is equal to the amount of absorbed sunlight. And the infrared to space equals the surface radiation minus the amount absorbed by the greenhouses. That's a net amount. Okay? And practically anybody could do the algebra to say that if the left sides are equal, the right sides are equal. Now this is a heat balance diagram, and I'm going to show you something about that heat balance diagram. Right in here on the left, you see you've got the incoming sunlight and the outgoing sunlight, but overall, the thing that's missing there is the greenhouse effect, which they haven't put in, but I did. And the greenhouse effect of 159 is equal to 398 minus 239. Those are in average watts per square meter. All those figures are in watts per square meter. Okay, I assume you'll remember that. This is an as-is situation. That's not the future, it's not the past, it's now. But we have to take one more little bit of science. And you remember in the previous drawing there, down at the bottom right, it shows 398 watts per square meter is emitted by the surface, and where in thunder does that number come from? The answer is it's calculable from the surface temperature by the Stefan-Boltzmann radiation law. Now, I'm not going to put that Stefan-Boltzmann radiation law there. I'm simply going to do a calculation, tell you what the answer is. The temperature that would radiate that amount is 289.45 kelvins, which is 16.3 Celsius. And don't get yourself wrapped around the axle about this precision. These numbers aren't known with that great precision. But anyway, you use the Stefan-Boltzmann radiation law and round things off sensibly. And if you need to look it up, just look up the Stefan-Boltzmann radiation law on the internet. I won't present it here, but every physicist knows it by heart. Okay, now comes future. What happens when the dreaded CO2 increases? Well, a climate crisis. Okay. IPCC does a couple of things, and I'm going to discuss one of them and then another one a little bit later. They make two predictions from the doubling of CO2. Prediction number P1 is that the radiative forcing, the increase in the greenhouse effect, would be 3.7 watts per square meter. They have used numbers as large as 4. And the most probable temperature increase at the surface would be 3 degrees C. You're looking at a lie. Here's how you're going to challenge your favorite climate guru, and you say, tell you what, I like that heat balance diagram that you had before. I would like you to have one for the future. So I'm going to show you the complete set of IPCC's heat balance drawings that they have made for the future, like 20 years, 50 years, and so forth. Here's the complete set. Now here's how you're going to make a buck. You're going to challenge your climate guru to make a heat balance chart for the future. And you put it in the form of a wager. So you say to your guru, pick a model, any model. Pick a time. 20 years, 50 years in the future, pick a time. And for that model, choose your pick. Just pick one of those points in there. On the left, by the way, there's a bunch of sort of individual lines there. Those are called SSPs, shared socioeconomic pathways. That's a fancy way of saying, I wonder how much CO2 people are going to emit in the future. And on the right, this is a bunch of predictions that were made in the previous assessment report. I didn't bother digging one out for the present one. But anyway, pick a point there. For that model and that time, find a heat balance diagram in the literature. You got 2 weeks. Or you've got a supercomputer. You've got printout from your supercomputer. Take the printout. Make up one of these heat balance diagrams. The numbers in your chart have to satisfy the conservation of energy, and $1,000 says you can't do it. Here's why those bets are safe. I'm going to go back to this business of CO2 doubling. This slide is one we had just a moment before. Radiative forcing is somewhere between 3.7 and 4. By the way, Happer and Weingarten come up with the figures more like 3, but I don't give a rat. That's good enough. Now, if the surface temperature increases by 3 degrees C, the surface radiation must increase by 16.5 watts per square meter. How can that be? How can 3 or 4 watts per square meter of, let's call it IR repression, possibly repress 16.5 watts per square meter that's increasing from the surface? It's a physical impossibility. But I'll go a little bit further. The IPCC only says that for doubling, 3 degrees is the most probable value, but they have a range. So the most probable value of 3 degrees C gives us, that's 16.7, just depends on how much accuracy you use. You have 16.5, can you read that? I'm going to have to read it to you. It's too darn small. Sorry, my mistake, but it's your fault. 3 degrees will give you about 16.5 watts per square meter in increase in surface emission. But they say the very likely range is 2 to 5 degrees C, and that would mean that the range of increased surface radiation would be something like 11.1 to 28 watts per square meter. And that's supposedly caused by 3.7 watts per square meter increase in the greenhouse effect. Huh? I mean, really? Okay, now we've talked about an equilibrium situation, which isn't about likely to happen. But IPCC also has some things that are sort of time dependent. And I'm going to show you those. And the feedbacks I'm talking about are things like, well, let's see. If we increase the temperature of the Earth, we're going to increase water vapor, which is going to increase the greenhouse effect due to that, blah, blah. We're going to change the absorption of sunlight by simply melting ice and exposing the Earth beneath it. So I'm just referring to some SSPs, and this is just color-coded nonsense. But see those numbers, SSP1 and so forth. Notice what I'm emphasizing there on the right. You got 1.9, 2.6, 4.5, 7.0, and 8.5 to the right of the SSP blank, you know. And those numbers just after the dash mean the total radiative forcing, which means the total increase in the greenhouse effect from all causes. This is the purpose right in here is just simply to define what they mean by those numbers. And there can be a change due to an increase in the amount of CO2 or from other greenhouse gases, change in the sunlight reaching the orbit, but IPCC says sunlight is constant, or change in the albedo or the reflectivity of the Earth. And all the models have the albedo increasing a little bit. Okay, now here is an example blown up so you can see it. It's one of 5 examples. Notice I've emphasized in the right part up there, SSP 3-7.0. SSP 3 is a certain presumed amount of CO2 emitted year by year. 7.0 is a total change in the radiation environment, watts per square meter. And they give you a scale here it's a bar chart with 4 different entries. The one way over to the right is change due to albedo, and they have it going negative. They have a change due to non-CO2 greenhouse gases, and then a change due to CO2, and you'll notice that CO2 is the larger one, and then the total. And all of these things are measured with respect to the pre-industrial period, which is 1850 to 1900. Don't say anything about dinosaurs, because that's not pre-industrial. Okay, what's missing? I'm going to add what's missing. See the scale I put on the left? The scale I put on the left is the increase in surface IR caused by those increases in temperature. So here we have 7 watts per square meter supposedly causing 20 watts per square meter increase in surface radiation. Okay? The IPCC chart says the increased ability to stop IR due to changes in CO2 and other GHGs and albedo is 7 watts per square meter, and that's somehow going to block 20 watts per square meter from going into space. I won't say a thing. Okay, now we come to the end. This is my summary in Tucson. Quick review. The greenhouse effect is real. Any model that does not acknowledge it is worthless. The effect, the greenhouse effect, can be and has been calculated from the radiative properties of the greenhouse gases. In other words, those graphs way back at the beginning of the cross-section versus wavelength. The IPCC's estimates of warming are inconsistent with their own radiative forcing, the increase in the greenhouse effect. And the warming of the surface cannot possibly be caused by the increasing CO2. Nobody's denying that the Earth is warming up right now. In fact, the best data show that it is warming a little bit, but it is not caused by CO2. There we go. You can get a hold of me at that one. No dartboards, please. It's okay. Thank you.
When I said I'd do make a short presentation of what's our message from the abyss, We have good measurements of Earth temperatures for the last 27 million years. They were produced in a paper in AAAS Science, real surprise, in 2020. I don't think the editors knew what they were publishing, and I think some of the authors really didn't realize what they were publishing. But Tom Gallagher, a paleoclimatologist, actually geological paleogeologist, took apart their data using acceptable methods, well-recognized methods, and discovered that CO2 is not correlated with temperature and a number of other things. Now, the data comes from from sea surface cores, sea bottom cores taken in the deep abyss, the deep ocean, and tiny mollusks or living organisms that feed on the snow, the marine snow dropping down. These creatures are, many of them, they form shells, but many of them are smaller than 1 millimeter. You can't see them. The video that I have here, Tom explains what is happening. It's a fairly long video, about an hour and a half, hour and 40 minutes, but it's extremely good in explaining how we can know that CO2 is uncorrelated, to a large part, uncorrelated to temperature. Cork went over that the association is very weak. Furthermore, that the biggest driver, other than the sun, of changing climate, it occurs in steps, and that comes from the change in ocean currents, which is the big store of energy, of solar energy, the change in ocean currents that occur with changing land masses. The paper divides 4 things: hot house, warm house, cool house, and ice house. We are now in the ice house. And what has happened is that the land masses have shifted around so much that we no longer have a equatorial Earth circulation of the oceans going around the equator. That circulation has been forced to go towards the North Pole or South Pole. And it's at the Arctic and Antarctic that we lose most of our energy to space. Sorry I don't have time, but I'll be happy to answer any questions if you have a wish to ask me any. We have 2 states of climate for the last 3.5 million years: dry, dusty, cold, and glacial. That's the default condition, the dominant condition for the last 3.5 million years. And we're in now a warm, wet, non-glacial period when vegetation and civilization thrive. Thank you very much for your time.